Hello and welcome to this exciting episode of Top Calc. In this episode, I ride an ATV, hold up a rope, and look at a small trailer. Now, this ATV that we're going to be looking at today is an Arctic Cat. It's got 5 gears, can run like the wind. It's got nice cushioning, handlebars, lights, everything that you can need. But it does also have an extra feature that is essential to today's episode. This ATV's speed and handling might be great, but it also has a hitch. This is quite a machine and quite the trailer. Time to move on to what we're really here about. While this ATV pulls the trailer, its speed always stays the same because it's directly attached and directly pulled along with it, especially when it's going in a straight line. But what if I take a rope, attach it to the ATV, to the trailer, and throw it over a branch? How will the trailer then move? We'll find out. As you can see, we've connected the rope to the ATV and to the trailer. Now it's time for the ATV to pull it and see how the trailer moves. But before that, let's check the math.
Let's jump right into this problem. So on the left side, we have the ATV, while on the right side, we have the trailer. From the back of the ATV, we have a rope that goes up over a branch and back down to the front of the trailer. For this problem, we're trying to solve for when the ATV is moving at 2 feet per second. What is the speed of the trailer? So for this, we need to consider what is changing in the problem. The first thing that's changing is the distance between the ATV and the trailer. The second thing that is changing is the length of the rope as it gets pulled over the branch. And to counter that is the change of the rope that is lost as it gets pulled over the branch. And finally, we have a cool little trick that we can do where we can put a line in the middle from the ground to the branch to essentially create 2 separate triangles, which can help us to solve this problem much easier, especially since these 2 triangles are right triangles, which allows us to use the Pythagorean Theorem. So for this problem, I've already measured out what we need to know. So on the left side, we have a leg with the length of 6.3 feet. We then have the shared leg in the middle of 8.5 feet and the total rope length of 23.5 feet. But what is still unknown is the length of both the hypotenuses and the length of the leg on the right side. To solve for the hypotenuse on the left side, we can take the 2 leg lengths and plug it into the Pythagorean Theorem. What this does is take 6.3 feet, square it, add that to 8.5 feet, square that as well, and then take the square root of the sums of that, and we are left with 10.580 feet, which is the length of the hypotenuse for the left side. Now there is a special relationship between the hypotenuse on the left side and the hypotenuse on the right side. This is because the 2 hypotenuses added together represent the total rope length, meaning that if we have 10.58 feet on one side, the other side must, when added to the original, equal up to 23.5 feet. Meaning that if we take 23.5 feet, minus it by the 10.580, we get that the other side has a length of 12.92 feet. Now, the final thing to solve in terms of the length is the leg on the trailer's side. And again, we can use the Pythagorean Theorem. For this, we need to solve and isolate the a variable. The first step is to remove b squared from the a side by minusing it. So we get c squared minus b squared, and then we must take the square root of both sides to remove a squared from the left side. So we're left with a equals the square root of c squared minus b squared, And all we have to do is plug in our hypotenuse for C, our other leg for B, which will result in our final leg being 9.730 feet. So now that we've solved all the lengths for both of the triangles, we now need to solve the rates. So the rates that we do not know currently are the rates of change for both the hypotenuses and the leg. We do know that this leg down here is going to be changing at 2 feet per second, and that this leg, the one that is shared by both triangles, does not change at all since it is measured from the ground to the branch, which is a static variable. The next thing we need to do is to calculate the hypotenuse's rate of change on the left side. And we can do this by using the Pythagorean theorem again, this time by using calculus, because we need to understand the rate of change for the hypotenuse on the left side. And rate of change is something that calculus can do very well. So when we first look at the Pythagorean theorem of a squared plus b squared equals c squared, we need to understand how those are changing with respect to time. So when we take a derivative of one of these terms, like a squared, we can use the power rule to take the 2 down from the exponent and minus 1 from the exponent, leaving us with 2a, and then we can times that by the derivative of a with respect to t, or really with respect to time. This means we have the rate of change right here. This represents a rate of change of the a variable of the a leg with respect to time, which means 2 feet, which 2 feet per second is that rate of change. So dA over dt is 2 feet per second. Similarly, dB over dt, the derivative of b with respect to time, is going to be 0 feet per second, which means that we can actually get rid of it, because if this is 0, this term cancels out of the equation. So now we're left with 2a times the derivative of a with respect to t equals 2c times the derivative of c with respect to t. Now what we have to do is solve for dc over dt, essentially the change of the hypotenuse with respect to time. So when we isolate this value, we can plug in the leg value of 6.3 feet times its rate of change of 2, divide that by the length of the hypotenuse of 10.580 feet, and finally we get the rate of change of the hypotenuse on the left side, which is 1.191 feet per second. Now, just like how the lengths of the hypotenuses were related, the rates of change are also related. For the amount that the ATV can pull the rope over the branch is the amount of rope that is pulled away from the other side. So if we gain 1.19 feet per second over here, we lose 1.191 feet per second on the other side. And this simply can be represented by taking the rate of change of the hypotenuse on the left side and making it a negative for the right side. Now it's finally time to solve for the rate of change of the trailer as it moves along this leg. Now, again, we can use the Pythagorean theorem, and we can get to the same place using implicit differentiation and taking each one with a derivative with respect to time and power rule and all that, and canceling out this rate of change, the dB over dt. But this time for the final thing, we need dA over dt. Since we are not looking for the rate of change of the hypotenuse, we're looking for the rate of change of this leg, which represents how this trailer is moving towards this point here. So when we figure out this equation, when we isolate dA over dt, we learn that we need to plug in 12.920 feet, the hypotenuse length times its rate of change of negative 1.191 feet per second, and then divide that by the leg length of 9.730 feet. And what we're left with is negative 1.581 feet per second. But this is not the end, because this is only the rate of change for this leg as it approaches, as it shrinks, as it goes toward this center line. Now, having a negative rate of change can easily be solved, since all we have to do is take the absolute value. This will remove its direction and allow us to get what its speed is, which the final speed is simply 1.581 feet per second. So while the ATV moves at 2 feet per second, the rate of change for the trailer is going to be 1.581 feet per second. So by using some calculus and a lot of the Pythagorean theorem, we were able to solve this problem and figure out the different rates of change and how they are affected and can be calculated across the triangle to finally get our result of this trailer's speed. Now let's go back and see what happens.
Let's see how it goes. It seems the rope has disattached and, well, on this terrible disappointment, I will see you next time.